It's working. Go. Ready? Hey folks, welcome to my talk.
Hello. Now will be talk from Mudit Gupta from Polygon.
Yeah, sure. Thank you. Thanks for the intro. So, hey everyone, I am Mudit Gupta. I lead security and smart contracts at Polygon. And if anyone doesn't know, Polygon works on scaling Ethereum. We are building layer 2 solutions powered by ZK Tech and Validium to scale up Ethereum. Today I'm gonna talk a little bit about how to hack a DeFi protocol and obviously how to protect yourself from those attack vectors. I'll demo it as well with perhaps the most famous hack, the DAO hack, where it all started really. And then if we have time, I'll let anyone propose their code that we can do live testing on. So if any of you have written any code recently, keep it ready. So to get started, let's talk about what makes a DeFi protocol and what the weak points are. So there are really two pathways to attack a DeFi protocol. One is the smart contracts themselves, and the other part is the traditional security side. So before I move on, one thing, like I was gonna have slides, but my dog ate my slides, so no slides for now. So I'll go ahead without slides, and I'll cover both parts a little bit, the traditional side and the non-traditional side. When I say traditional, I mean Web 2, and non-traditional is Web 3. Traditional side is something which has been overlooked in this space a lot, but we see like the big hacks that are happening are more on the traditional side than the Web3 side. A good solid example would be multi-chain, which like they literally released their story today. If anyone hasn't read their tweet, it's hilarious. Go ahead and read it. The TLDR is that multi-chain claimed to be an MPC bridging protocol, but turns out all the MPC nodes were running in this one guy's cloud server. So it was basically one guy running multiple nodes. And then that guy got picked up by the Chinese government. The team lost contact with it, and they had no idea what to do with the servers now. So this guy's sister steps in and handles them. But then not the Chinese government, someone moved funds from the protocol to some other address. Allegedly, the Chinese government, since that guy is under their control. And then the sister tried to white hack it and got into the brother's laptop, opened their cloud account or whatever, and moved the funds somewhere else. Surprise what? Next day, the sister goes missing as well, apparently picked up. And now all of the money is gone, and nobody has no idea where the money is. You can guess where the money is, but it's an interesting story of a bunch of failures. If we go down, they failed at multiple steps. The first step is, firstly, why did an MPC protocol had all of their servers in one single guy's account? So that's one traditional security failure, has nothing to do with blockchains. Then the other failure is, why did that guy's sister have access to their computer? Like, great OPSEC. Like, you are securing millions of dollars, and just your random family member can access everything. Then their like emergency response plan or whatever, sister moves funds to her own address. Voila, like how successful that was. She also gets picked up. So bunch of cascading failures there, but moving on from there. Other attacks in the space, the big ones, the Ronin bridge attack, another traditional attack, which was, Ronin was another bridge, multi-party bridge, but they were a 5x9 multisig basically, not a multisig, but a 5x9 MPC protocol. The problem with them was similar. 4 of those 5 were running on basically one center, one server, or one collection of servers. And those servers had access to the 5th server for whatever reason. So the attacker only compromised one DevOps employee of that company who had access to all the 4 servers, and those 4 servers had access to the 5th server, and voila, everything gone. Again, there are many traditional security failures here. One is 4 servers on the same like cloud account or whatever, and then second vector would be 4 servers having access to the 5th server. Then the servers being accessible by a DevOps employee, and then the DevOps employee falling prey to these phishing attacks, another traditional security failure, and a bunch of these. So a collection of these traditional security failures led to these hacks. If any one of the levels would have been fine, they would have been fine. Security is all about having layers of security. So those are some examples of traditional. Now we'll move to some more blockchain side, where it is mainly things on the blockchain itself, on the smart contract side. You manipulate the smart contract to do what you want, and voila, you have free money. So not free, but almost free money. There are numerous examples of these as well. One of the biggest ones recently that happened was Nomad Bridge. So bridge seems to be a good theme here. A lot of bridges getting hacked these days. But Nomad had a logic issue in that, a bug that got slipped during audits, and that led to an hack. Unfortunately, we don't have much time to go into the details of that. But similarly, another big one that happened recently was Euler. So Euler is not a bridge, so that's something unique about them. But what Euler did was they added a function which is arguably not as useful to the code to increase the functionality. But guess what? That function had a critical bug. So some key lessons here. One is, like, if you're working with smart contracts and big chunks of money, avoid changing code and avoid adding features that maybe are not necessary, because these features may end up resulting in hacks like this. Euler did 6 audits, but they still got wrecked. And the reason is, like, one, first of all, these upgrades maybe were not necessary. They were taking additional risk. Every upgrade you do is additional risk. But also the fact that despite 6 audits overall, there was only 1 audit done on the final code, on the last upgrade. So saying 6 audits, it's maybe a misleading word. Like, only 1 company audited the buggy code, and it's very easy to slip through. So those are some examples, but now let's imagine from our scenario. As an attacker, how would you attack this? So if you're going the traditional paths, there are like a bunch of guidelines and tutorials already. You would probably start with finding attack vectors you can attack. So centralized point of failures, it might be multi-sig key holders, it might be MPC servers, it might be hot servers holding keys for exchanges, something like that. And then you would probably try to do phishing. That is the most easy attack path right now. For on the counter, you should do phishing awareness training for your employees, so then don't fall prey for it. But you would likely go down a phishing route or a social engineering route. You can also try pen testing, the regular good old stuff, getting into the server. But these days, that path is usually closed off. So you have to go the social paths. Humans are really the weakest link in security. You can secure computers reliably. Securing humans reliably is super hard. Just get them drunk and it's game over. So that's very hard part, which you would attack. But now let's also move a step beyond. Let's get into the DeFi things. Let's get into the Web3 stuff, which is arguably more interesting and arguably more accessible and easier. If you just have the right knowledge and you are looking at the right place at the right time, you can do it. And similarly, like from a security point of view, from the reverse, people have to understand that as a security person, I have to get it right every single time. I can't let any bug go through any of my things. But as an attacker, I only need to attack one weak point. I only care about one. So although from a security person, I have to make sure I secure every single bit, the attacker only has to look at the critical pieces and exploit what they can. They don't need to go through the whole piece. And that's the main strategy, both to doing audits to prevent these attacks and also to attacking a protocol. If you start auditing a whole protocol, if you want to attack it, you won't make it so far. You just need to focus on the key bits. I think I'll showcase it with a live demo. If I can figure out how to exit the full screen. No, I press something else. Okay, anyone knows how to exit full screen on Mac? Or switch tabs? Anyone? Okay, no. Search open. And not this one.
Switch tab.
No, I have full screen. I don't know how. Maybe function.
Usually it was.
And I clearly don't use Mac. I'm a Linux guy. Oh, we got it. Thanks a lot. Okay, we won't go full screen this time. We'll stay here. So this is the DAO repo original contracts that got wrecked. We'll go through these. Have been a long time since I looked at this code, so bear with me, but let's go through it. So if you are trying to attack any smart contract really, what you'll do is first of all, open the source code if it's available, which it is here. And then we'll go through the code and look for most critical pieces. So first of all, I'm just glancing through the code for some highlights and make sure I'm at the right file. And once I verify that I'm on the right file, it seems like it. Big enough code should be the right piece. And like basically, you have all of this code here. You can, from an attacker perspective, so I'm really now looking at this from an attacker's perspective. I don't know anything about this code base, let's say. So I look at the source code, I find the most interesting file, I open it, and then what I find for is value transfer. Where is value being transferred? So to find that, you look for a few things in DeFi smart or Solidity smart contracts. One is the transfer function, which literally means transfer value. One would be the send function in Solidity, which transfers ether. One would be the .call function in Solidity, which makes arbitrary call and can also pass ether. One would be approve function, which is used in ERC20s, and so on. So these are the critical points from where we'll walk backward. So let's start finding these things. And if I can find how to search for it. Okay, I found it, yes. So let's go with dot transfer. Okay, this is a different keyword than QWERTY. Okay, so let me also add. Oh, shit. Okay, I can't find the opening braces, so we'll search through this. Okay, there's one transfer function here, which is sending, it is taking tokens from the user and sending it to 0. So that's not very useful for us. We want to take the, we want the contract to send us the tokens, not send itself the tokens. So we'll move forward. Same thing. This is an internal function. We'll skip over. Super transfer, not very useful. No. So basically, as an attacker, that's what you do. You go through these pieces, just looking at where the value is being transferred. And so far, I went through the whole contract. Transfer is not transferring any value. So I'll go with call next. It would go really faster if I could find the opening braces, but okay, dot call. Okay, this one is interesting. So this one obviously transfers value of P amount to the recipient. Now, this is one value transfer. Now, let's notice where it's happening. It's happening in execute proposal. So I guess, so one thing you should also do, which I didn't do, is if you're trying to attack something, read like a brief overview of what the contract does. So you know what you are looking for and what is the expected functionality. The DAO, as name suggests, is it has features of governance. It's an autonomous DAO. So it has features like executing a proposal, proposing a proposal, and things like that. So this is proposal execution. This is definitely one way to attack it, but a proposal, if it has to be executed, it needs to pass through governance. So governance will need to approve this, and then only then we can get funds from it. So if I have to exploit this, I will go start. Now I found one value place. Now I'll keep walking backwards. Now how can I execute this value transfer? By having the vote pass. How to get the vote pass? Get the governance through it. So I will start looking into how can I manipulate the governance to get my votes here. most likely in this scenario, I will not end up as a positive result because we have knowledge that this was not the attack vector that was used on the DAO. So I won't spend much time here, but I would have gone reverse from here if I was actually looking for an attack to see if there is any path I can enter and then walk back down. So we'll go to the next call. This is withdraw. This is interesting. I'll come back to this, but let's see what else we have. We have new contract. New contract is not too interesting either because this is blocked here. So withdraw is the most interesting bit. So withdraw is used by token holders to withdraw their funds. And we know this was the attack vector that was used to hack the DAO. So we have some pre-existing knowledge, but we'll follow the same process. Now we found a value transfer in the contract, one critical bit, and we know if we can break this, we'll have our funds. Let me figure out if I can zoom in the screen. Probably not. So we'll stick around. Okay, I found it, I think. No, I think that's open, maybe this way. Yeah, it's fine. Okay, it worked. Hopefully people can see it now. I can go maybe one more. Okay. So withdraw is the most important bit. We found the value transfer here. So what this line says is transfer all money, transfer this much amount of money to the user. That's all it does. Now we see like how is this money coming? Where is this money coming from? So it's the money is coming from your balance. So user needs to have an actual balance, and then pro rata based on their balance, they get the balance out of the contract. So if I hold 5 shares or 5 balance, then actual balance by total supply. So basically you can imagine like I get my balance back from this contract, simplifying it. So it checks for your balance and then sends you the money. This line not very useful. We can ignore. We assume we are not blocked by the voting. So now you have to have some solidity knowledge as well to find these issues, which is a precursor if you want to get into DeFi. But once you have the basic knowledge, you can see something that is wrong here. You'll only see it if you know what call does. And what call does is it passes over the execution flow to the callee. So message sender here, I'm making a call to the message sender that, hey, knock, knock, here are your funds, and now you do whatever you want with these funds. In most cases, and in the expected case here, the person, message sender will take the funds and say, okay, thanks for the funds. Now you can do whatever you want. I don't want to do anything else with these. That's the expected use case. But what this message sender can also do is be malicious. So it can, when it gets the call and it gets the fund, it will say, okay, thanks for the funds. And I have the control now, you can go buy. And now since I have the control, it will go back to this contract, call the withdraw function again, and innocently go there, knock the bank and say, hey, I have this balance, can you give me the money I hold? And the bank would go here, check, hey, okay, this guy has some balance, hey, here's your money, go. And then you'll get the money, you'll get the control, you'll go back to the bank again, maybe to a different branch, knock again, say, hey, I have balance in your bank, can you give me the money? And the cashier would be like, okay, let me check your balance. Okay, you have some balance, here's your money, go. And the issue here, if you have seen, is the bank is not updating the user's balance. It's just giving them the money here. They do update the balance, but they update it down here later. Balance message sender equal to 0. So they do update it, but they update it after giving the money to the user. So you have this weird edge case in between, weird time in between, where you have already gotten the money from the contract or from the bank, but the information hasn't been propagated to other places yet. The other branches of the bank don't know this yet. So you are basically exploiting it by reentrancy. You take the funds once, you get the control, you go back to the contract, you ask for funds again, and the contract will give you again because it doesn't know that it hasn't updated its state yet. The information has not been processed yet. It's like a concurrency problem in Web3, in Web2 world. If you do it in a bank, it won't work. As soon as you take out money, all of the branches of the banks will know, okay, your balance has reduced. They'll reduce it before giving you the money. Maybe make you wait 2 days before giving you the money, but they'll reduce it first, which we failed to do here. We gave the money first, and then we're like, okay, we trust the user, we'll reduce it. Where is he gonna run? But yeah, he ran back to us, took more money. So this is one practical example, and one specific bug you can look up in DeFi smart contracts. Just start looking for value transfer, go back from it, how did this value transfer happen, and try to hijack the process at any stage. If you can hijack here or the parent function, doesn't matter. Once you hijack, you just follow the path and you take the money out. So this is how you start. Now imagine like this doesn't work. Like I go through everything. None of these like value transfers are really exploitable. So what do you do then? Then you have two choices. Either move to the next target. There are plenty of fishes in the sea, or you go deeper. Now, when you go deeper, so you have the first stage, the value transfers you have verified. They are all fine. The second you would do is try to see where it's integrating, where the external input is coming, and try to attack that. So if it's a DeFi protocol, it's maybe using oracles. See if you can target that and do some price manipulation. You can do maybe like unique pool price manipulation, sandwich attacks, and things like that. So you go a step beyond. If you can't find a hack here, you go one step overboard and you try to manipulate a system that this protocol is depending on, and it has wrong assumptions about that system. And if that doesn't work out, then you probably have to do a full audit if you still want to attack this, or you can go for a different contract. Obviously, we are talking about bug bounties. We are finding bug bounties here. There is no hack we are suggesting. So you'll just open Immunify, find the other protocol, and try to find a bug bounty there. So that's the DAO hack and one practical example. Now, do I have time? I have a few minutes. Anyone has any contract of theirs that they want me to go live? Okay. That is too big to go live in 10 minutes. Any simpler one, I would say. Not really. So maybe I can just talk about the Polygon bridge a little bit since you brought it up. And or not maybe the Polygon bridge. I'll talk about bridges in general because that's a very interesting topic. And we see bridges keep getting hacked again and again and again and again. So it's clearly something people haven't figured out how to do properly. Not everyone at least. So in bridges, I really see them that they are of three types. One is a decentralized bridge, which derives its security from the parent chain. So a bridge basically bridges token from chain A to chain B. And in most cases, there would be a major chain, chain A, and a child chain, chain B. Like if you talk about Polygon zk-AVM, the major chain is Ethereum and the child chain is zk-AVM, which is a layer 2. So a decentralized bridge that we have here derives its security from Ethereum completely. The only two ways to attack it is either find a code vulnerability, a logic vulnerability, or just attack Ethereum. So the way it works in broad sense is that you generate proofs of something happening on one chain, and then you verify those proofs all automatically on the other chain. And once you verify that I moved my token to the bridge contract on the parent chain, then the child contract here can release tokens. So it's all proof-based. You have proof something happened on chain A. If it can be proven on chain B, it will give you the funds. So there is no centralization risk, no centralized party. You can generate your own proofs. You can submit your own proofs, and so on. The only possible bug vectors here are really like attacking Ethereum, let's say, is hypo and is assumed to be not possible right now. So the only attack vector that remains here is implementation risk. If there is a bug in the smart contracts which can exploit this, which is a very valid issue. So you have to be careful about it. But these are generally believed to be the most secure bridges. And good example, as I mentioned, is the Polygon ZK EVM bridge here. The other type, the second type of bridges are the MPC bridges, the multi-party compute bridges. Here, usually there is a set of nodes which pass message from one chain to another. And if majority of the nodes agree, then the message is bridged. Here, like the nodes can be in config of 2x3, like the Harmony bridge, which got wrecked, like 5x9, like the Ronin bridge, which got hacked, like multi-chain, which I would say 1x1, which again got hacked, and so on. So there are like these MPC protocols, and the way they work is you do transaction on one chain. These nodes look at that transaction. They are running the nodes of these chains, and they once the transaction happens, they post it on the second chain. They say, hey, this one transaction happened on there, so we should do the corresponding bridging. If enough nodes post the same message, then it's actually executed and the bridging happens. So it's basically a voting mechanism. In theory, it can also be secure for two reasons. One is technically it's easier to implement than the decentralized bridge. So the risk of smart contract hack here is lower. And as we have seen, the MPC bridges that have been hacked have mostly been hacked via the traditional exercises. The smart contract hacks have not really affected them because it's a relatively easy thing to build. So on the traditional side, obviously, if you do a 2x3 like MPC, if you do a 5x9 MPC, if you do a 1x1 MPC, it's not secure. You need to go higher. Polygon POS bridge is a mix between MPC bridge and a decentralized bridge, in the sense that there still are proofs, but the message passing happens in an MPC layer. And for that, we have 100 validators, not 1, 3, or 9. So there are many decentralized validators, and we are not the ones that are running all of these validators. They are run by the public in a decentralized fashion. So that's a much more secure and harder to break way. So that's one type of bridge. In this bridge, the attacking vectors are really the traditional side. If you can break the MPC, if you can get into the servers that are running these nodes, it's all yours. And this is what we have seen in the past. So if you're running a bridge of this type, make sure you pay attention to your traditional security, make sure your key management is secure, make sure you have a high ratio of MPC, and then you would likely be fine. The third type of bridges are really the centralized ones, which are like just one entity. For example, you put money in Binance on Arbitrum and you withdraw on Ethereum. You have essentially bridged money from Arbitrum to Ethereum, but you used a centralized bridge, which was Binance. Here, all of the security depends on the traditional security practices of Binance, key management, hot wallets, and so on. There is no smart contract involved. It's all traditional security. Another example of this would be the Avalanche bridge, actually. Avalanche bridge is an EOA, actually. It has no on-chain multisig or anything. It's 1x1 EOA. But off-chain, they have an MPC algorithm, which is, I think, 3x4 or 4x4. So arguably not sufficient, but at least something. And they do it on Intel SGX, so it's relatively secure tech-wise, although they can bump up the MPC numbers, and that would be really appreciated if anyone from Avalanche is hearing. So those are the centralized bridges, I would say. If you want to attack those, or if you want to secure those, then again, you have to focus on traditional security 100%. Make sure your key management is safe. Make sure you are not storing secrets in plain text on your hot servers running in some DevOps account. Make sure access to those servers is also secure. Make sure your DevOps employees are properly trained for phishing awareness and things like that, so you don't get tricked. And these are basically like the three types of bridges and three different security mechanism there. For the decentralized bridges, just make sure your application is secure, get a bunch of audits, get bug bounties live, get these audit contests done by Sherlock, Code Arena, and these companies, get a lot of independent reviewers look at it, have a lot of fuzzing, you can try for formal verification using Satora, but most importantly, just have an open security mindset and have good test cases. Most of the things can be caught by test cases, honestly, and just having an open mind. Then the other side, the middle layer where you have traditional security as well as smart contracts, you have to do both. So these are the bridges that most often get hacked. You have to be secure on the smart contracts, which is relatively easy to do, and you have to be secure on the traditional security side. The only saving grace here is that it's all very common, very documented. There are known best practices, so you can just follow the best practices and be done with it. And the first one, the centralized bridges, like maybe just stop building them. If you are building them, then make sure your traditional security is fine, and then you'll be fine. It will all be happy. We'll all be happy. No more hacks, and we'll all live happily after. And that was a quick, short talk. If anyone wants to reach out to me, then they can reach out. My contact details are on my blog, mudit.blog. I can't find the letters here, but you get the idea. Oh, I managed to type it. Not right still, but yes. You can contact me through my blog, and happy to talk. Thanks, everyone.
Thank you. Thank you. Any questions?
Anything about attacking a DeFi bridge, DeFi protocol, or security, or Polygon, anything. That we don't do. We keep it there.
Thanks for the great talk. My question was also on-chain attacks on bridges, like Nova protocol, for instance.
Yes.
The issue was synchronization of Merkle root on either side. So how do you try to model that also into account?
Yeah, so that would fall in the like decentralized bridges category. So it's more a smart contract risk slash software risk. If there is a buggy software, then obviously you are going to lose money. And it's super complex to actually build and secure these bridges, which people underestimate and say like decentralized bridges are the best. Yes, in theory they are the best, but they are also the hardest to secure from a code point of view. So that's why I said you need good developers who understand security and will build this thing ground up with security in mind. You need them to write good test cases. You want fuzzing in there. You want to get in some formal verification if you can, although it's hard for these complex cases. You want to do good audits with reputable vendors. You want a good bug bounty program. Polygon has a very successful bug bounty program. We offer bounties of over $1 million, and we have had very, very, very interesting findings through that, which all auditors missed. So yeah, just those are the ways to secure it.
So just a follow-up question. In case you said Euler example that adding another function creates this security threat vector, how can we modelize in real time? Let's say if we want to change the protocol using a new proposal, how can we modelize it? Is there possibility to, let's say there is formal verification, other aspects?
Yeah, so a couple of things there. One is like, if you have to do it, then there are ways like for continuous integration. One is obviously your test cases should always be passing. If you go formal verification route with Satora, you can have the same rules be verified every time. And like you just get audits ideally from the same people, so have the whole context. But in the first place, to be honest, you would try to not upgrade a contract unless it's absolutely mandatory. So upgradability is a double-edged sword. I like upgradability because it allows you to get out of sticky situation. If you find a bug in a contract, you can upgrade it, you can save your life. But I don't like upgradability when it's used to add a new tiny feature. Then it's always about risk management. Whenever you add a feature, you're taking on risk, and you have to ask yourself, is that feature worth the additional risk or not? Oftentimes, at least for me, it might not be worth the risk.
Hi there. My question is concerning the future of like what's next. A few years ago, we had cross-atomic swaps. Now we have the new innovation of bridges. What, in your opinion, is going to be so groundbreaking that comes in the next few years?
Yeah, sure. So that's a very big question. For me, there are two things here. One is like I really believe in a multi-chain future. Not the protocol, but multi-chain in the sense there are many different independent chains that will live at the same time. But I do not really believe in a cross-chain future. I don't think people will be moving funds, doing transactions on two chains atomically. I'm not a big fan of that just because of the complexity of that. And I like to compare this with the real world. So there are many, I like to think of chains as cities. There are many major cities in the world right now, and you can go from one city to another using a flight or maybe a bridge if they are close enough. So you can, it's a multi-city world. You can go across different cities, but you can't have your leg in two cities at the same time. It's just not possible. It's super complex. So I like to think of it, that's this analogy I use. And the other thing I'm really bullish on, and I think is going to be big, is ZK scaling technology, because scaling is a big bottleneck for our tech to grow. If we can solve this, we will immediately have lots of new interesting use cases that are just not viable right now because it's too expensive. If you look at internet was never free. Internet is still not free, but it's affordable enough that nobody cares how much it's costing. Every time you open a web page, the website host is paying money to their web host to serve you the page. The data on internet still costs money, but nobody cares. Every website is free to browse. Every user has an internet pack. They don't pay per website visit or anything like that, just because it's so cheap that it can be bundled together. And that's where I think ZK tech will take us, that transactions would be so cheap that everyone would just use blockchains without worrying about costs. Anyone else?
Thank you, Mudit Gupta, for your talk. And now is time for our next speaker.